Hey everybody, Dr. A here, and in this video we're going to be exploring another example of how to use deflection formulas. So let's go ahead and get started. In the given information, we're being asked to compute the deflection at the midspan, and we're also being told that the flexural rigidity, which is the product of E times I, is constant. So here we have a simply supported beam that's 4 meters long, and it's subject to a linearly increasing load. So that's a triangular shaped load. It starts at 0 at the left side and it increases up to 20 kilonewtons per meter at the right side. All right. So how do we tackle a problem like this? Well, notice that this problem is not asking for the maximum deflection. It's asking for the deflection at the midspan. So if I were to sketch the deflected shape of this, okay, let me draw it a little bit better for us. So if I were to sketch, oh man, that got worse. If I was to sketch the deflected shape of this, this would be slightly lopsided, okay? So delta max is not at L over 2. So that's one thing to keep in mind, but we're looking for the deflection at L over 2, okay? Now, I'm going to be referring to a deflection formula from Appendix C of the Hibbler Mechanics of Materials textbook, okay? Now, if I refer to what is given there, I'm going to need to use the equation of the elastic curve and substitute x equals 2 meters into it, okay? And again, the reason why I'm going to have to do that if I'm using the Hibbler Mechanics of Materials Appendix C formula is because in that formula, in that table, we only have given to us the maximum deflection, which is at x equals 0.52, which is not quite at 2 meters. So it's not quite half of the length of the member, all right? So this is a good exercise on how to use the elastic curve when we need to use it, which we might need that sometimes, okay? So the formula that we're given is negative WX over 360 EIL, okay? And all of that is going to be multiplied by a big term, 3x to the fourth minus 10L squared x squared plus 7L to the fourth, okay? And so what we're going to do here is substitute in our values accordingly. And remember, the negative sign here indicates a downward deflection, all right? So what we're going to do is substitute in x equals 2 here. So what I'm going to do is I'm going to say delta equals, and I'm going to substitute in 20 kilonewtons per meter times 2 meters divided by 360 EI, and then L is the total of 4 meters. And then I'm going to multiply that by 3 times 2 meters to the fourth minus 10 times 4, didn't mean to scroll there, 4 meters squared times 2 meters squared plus 7 times 4 meters to the fourth. Okay, so I've substituted in all my known values, a lot of 2's and 4's, all right? And so I'm going to be able to say delta when x equals 2 meters, again, that's function notation, is the following. I'm punching this in my calculator right now, so maybe you punch along with me and do it carefully because this is really easy to make a computation mistake. All right, plus 7 times 4 to the fourth power. Okay, and we're going to say times 20 times 2 divided by 360 divided by 4. And so I end up getting didn't mean to scroll again, 33.3. Now, what kind of units do we get here? You should get kilonewton times meter cubed over EI, and that's going to be deflecting downward. Now, how can we check those units? Well, let's look at it. Inside the parentheses, each of these terms has units of length to the fourth power, all right? And so if you have length to the fourth power in this big parentheses times a length, that's length to the fifth power, right? But then you're dividing by a length here, so that knocks you back down to length to the fourth power. And then you're multiplying by force over length, so that gives you force times length to the third power, okay? So that's going to conclude this example. Again, this is a nice example because it gets us an opportunity to use the equation of the elastic curve here. So if you found this video helpful, please hit like and subscribe and be on the lookout for the content like this. And shout out to the Charles Hibbler, I think is Russell Charles Hibbler, R.C. Hibbler, Mechanics of Materials, Appendix C. All right. Again, be on the lookout for the content like this. Thanks for watching.